So hi everybody, I am an undergraduate at MIT, and for around the last year and a half or so, I've been working in the Julia lab here on this problem of automatic differentiation of programs that contain discrete randomness. And there's also an associated package called StochasticAD.jl that I'm going to demonstrate a bit today. And everything I'll talk about today has been joint work with a bunch of wonderful people, many at MIT, some in Sweden at Chalmers University. So what am I trying to do here? What is this problem about? Fortunately, this slide is blank, but I have a code demo, or I would like to start with some code. So what sort of problems are we interested in? So it's a little hard to code and hold this. Maybe I should use this. Testing? Okay. So in standard automatic differentiation, the user might write, a deterministic function like this, right? This is like one of the simplest deterministic functions you can write. You can square it. And Julia has great, and then you can, evaluate this function. I'm sure it's all familiar to you. And Julia has great tools for now asking, what is the derivative of this function? So you do something like, something like this. And you get that it's 2x, which is 1. So in this talk, we're going to be in the business of automatic differentiation. So we're going to be in a similar job to this package is right here, which is that it's going to take in a user-written function f and some input, and its job is to produce now the derivative rather than the original function. What's new here, however, is the class of function we'll consider. Maybe I'll just make this very big. So I'm going to use a new function here. I'm going to use this capital letter X for reasons that'll become apparent later. And this function might maybe return the result of a Bernoulli flip with probability p, okay? So now I can run this function. So a Bernoulli flip is basically like a coin flip. So it's probability p of being heads or 1 and 1 minus p of being tails. And I can sample from this random variable. I can run this function. Sometimes I get true or 1. Sometimes I get false or 0. And we would like to now have such a function as an input for automatic differentiation. So I think probably, maybe from your phrase, I did a little work here to even explain what it would mean to do automatic differentiation in such a setting. And then, what would be a useful primitive, and then how do we do it, right? So, that maybe gets us a bit closer to the problem at hand. More formally, deterministic AD is about this transformation, starting with a function, can we compute its derivative? In the stochastic case, we can think of having, rather than the deterministic function, a family of random variables, right? That's why I use this capital letter. Now indexed by some parameter p. That's how you can mathematically think of that program I wrote down. And now, what might be a useful quantity we'd want to differentiate? Well, we might be interested in differentiating statistical quantities of this program. For example, its expectation. So this might be something I'd want, okay? But if I just made this the goal of my automatic differentiation tool, I'd be in a lot of trouble. Because, why do people write stochastic programs? A big reason is because, they estimate intractable integrals. They sample from something you can't write down in closed form. So you can't just go and say, I'm going to write down this expectation as a nice continuous function and differentiate that using standard tooling. Instead, you'd really like to remain in Monte Carlo space, right? You'd like to make actually a new program that's also random. But rather than obviously like the original program estimated as expectation, you'd like the new program to now estimate this quantity of interest, the derivative of the expectation. And that is precisely the goal of this problem of stochastic automatic differentiation. So this object here in machine learning is often called a gradient estimator. This is a problem a lot of people think about. And this is precisely the primitive we'd like to offer in our package. But we have a particular focus now on discrete randomness. So we'd like to handle even things like coin flips or dice rolls. Okay. Are people comfortable with that? Good? Okay. So discrete stochasticity appears a lot in practice. So you just, like a couple talks ago, I had a whole talk about these jump problems. Often they might arise in like biology and like these chemical reaction network systems that look like this. They have a discrete form, which is often the form you want to use in these systems which are extremely noisy, where the noise is like on the same order of magnitude as the signal. That's often there might be discrete stochastics underlying that. There are agent-based models, so this is actually the game of life, which is actually deterministic, but many agent-based models have discrete stochasticity and like decisions agents are making. And actually one application I'll talk about later today is actually taking the derivative of a Metropolis Hastings sampler. So these are like samplers of distributions, and they involve this step where you like propose a new sample, and then you either accept it or reject it. So that's really just a Bernoulli in disguise. Okay, what's next? Okay, so our focus is kind of going to be on discrete randomness, but now I want to talk a little bit about the continuous random setting here, because it turns out that people already have a solution which in many, many cases they're very satisfied with, and it's used all over the place, in all sorts of disciplines. So the old school word for it would be the pathwise derivative. In machine learning, it's often called the reparametrization trick. It's used, for example, in, variational autoencoders. Yeah, so let me actually ditch my discrete program for a second and just write something continuous. Okay. And this time I'm going to sample from a continuous distribution dependent on this parameter p. So picking this exponential distribution, its density function follows decaying exponential. And I can also just sample from this just so you can believe it works. Okay, and we're getting some samples. Okay, now I'd also like to shift perspective a bit, even with like my original function f. And start thinking about differentiating these in terms of these objects which you might be familiar with, like these dual number objects. How many of you are familiar with this concept of a dual number? But basically, it's just a pair of like the original value with its derivative. And often this is how people implement AD in the forward direction. And you can think of differentiating f as actually just plopping this dual number into f. Okay, you can see that like this number just goes as like the original value, and this as the derivative, right? And now you can think now to this continuous function here, and actually this reparametrization trick is already implemented in Julia. It's implemented in all the machine learning frameworks, and it means that if I actually just plop this dual number into this continuous random function, what I get is a random sample for the original value and another random sample for the derivative. So in this talk, I'm not going to have time to explain what the reparametrization trick actually does, but the point is somehow it's come up with like a pairing of original samples and somehow derivatives of these samples, such that just like you could average this first column and get the expectation of the program, you could average this second column and get its derivative. That's pretty convenient, and it doesn't change any of the usual infrastructure for AD. Like you can see, it still uses this familiar dual number concept. Does that all make sense? Okay. But now, the obvious question is, if I think about a function like this, what's going to happen if I plop my dual number into here, right? Are there any guesses?
0 epsilon.
0 epsilon. That's a good guess. Yeah. And also, so it's always 0 epsilon. So if our goal was to differentiate the expectation, then we're in a bit of trouble here, right? And just like, again, I'm not going to explain this pathwise derivative reparametrization type thing, but just like the tagline is like sort of the idea is to use the same random numbers, the same random seed, same random call as you got in your original program, your primal program, for the derivative. So you differentiate the programs using the same random numbers. And this is actually like a well-defined mathematical object. Like even in the case where we're getting all zeros, it's well-defined what we're doing here. It's sort of this derivative which is in some sense like almost surely correct. If you're familiar with this like notion of almost sure from probability theory. And there's actually this funny issue on like the JAX repository where someone wrote a program that looks like this. Okay, so they call it a rand call, and they had like this branch where the branch actually the probability of each branch depends on the cosine of the parameter, some input. And they were complaining that JAX is just giving zeros for this. And actually, I would say that Matthew's response here actually has a a fair point, which is they are computing a very valid mathematical object, this almost sure derivative. That's what the reparameterization trick computes. The only problem is that for our use case, we want something that solves our problem. We're actually interested in differentiating the expectation. So this is a fine mathematical object, but it doesn't, it's not what we want here. So how can we fix this problem? Okay, and the other, the double whammy here is also when they work, they're great. I already said this. People love pathwise derivatives, these reparameterization trick derivatives. So we're really missing out on something in the discrete case. Okay. So what should happen for a Bernoulli random variable, right? We would like to get something out which somehow describes, the quote-unquote sensitivity of this value to its input, right? Basically, what is the dual number picture saying? It says that tiny changes in, push forward into, tiny changes out, right? But what should the picture be for a Bernoulli random variable? So actually, I'm going to upgrade from these dual numbers to these stochastic triple objects. Let me remind you again what our function is. And this is the numeric type that's provided by our package. And if we plop this into our Bernoulli, we'll either get something anticlimactic or what I want. Okay, this is what I want, okay? So it's telling you, this is sort of just even the original thing, it's sort of it's sort of fanciful pretty printing of this number. Really, we're not storing any epsilon, we're just storing these numbers, but it's saying that you got a 0, your coin was a tails, but with a tiny probability, it's like the probability of a flip in the coin that's what's differentiable in epsilon, okay? So this is what your number is telling you, and you can actually collapse this into a derivative estimate of 2.5. So if you actually were to take the mean of the derivative contribution of, hopefully I have the brackets right there, a bunch of times, we'll get, what we'd actually expect, right? The expectation of a Bernoulli is equal to P. Okay, but maybe this is not the most, impressive result in the world, right? We'll hopefully get to something better. So yeah, we've seen this. Okay, now I just want one slide maybe motivating why we take this picture to the estimation of gradients of discrete random programs. So I'll go through this in a fast, and it's fine if not everything makes sense. But for think of a random variable like a binomial random variable. This is like a sum of Bernoullis, sum of n Bernoullis of each probability p. You can think of sampling from it through this, it's called inverse transform sampling process, where you sample a number uniformly between 0 and 1, and you sort of look up the value on this step function. And what you get on the y-axis, that is your sample from the random variable. Okay, so this curve here is actually the inverse CDF of the random variable. And now we can ask, what happens in this parameterization if I perturb the probability slightly. So here I have p of 0.6, and then this point, this is the x point here is the CDF value of 5 and so forth. And if I perturb slightly, what happens is where these step occurs change. So the reparameterization trick, which sort of differentiates using common random numbers, is sort of differentiating this curve point-wise at every point in the x-axis, and you can see how if I make this perturbation smaller and smaller, that leads to the situation of getting all these 0 gradients, right? Whereas this picture motivates, now we think about, say we sampled and we got a 5. So we know our random variable is like somewhere over here. And now we think about perturbing p, like conditional, or like the random number being somewhere here. We can see how like maybe there's like some measure moving from the possibility of a 6, the possibility of a 5 to the possibility of a 6. Like we originally got a 5 here, but now we got a 6. So maybe the right picture here is that actually there's like a weight of going from a 5 to a 6, right? And then I should also mention for like completeness here that like probably the most popular technique for gradient estimation, especially in like machine learning, reinforcement learning, is this approach called the score function method, which sort of just looks at like the derivative. Another approach you might think of is like taking the derivative of the probability of the 5 and so forth, and doing that. But the claim is that maybe this approach here, which might look like this, like we could have gotten x, but now we originally got an x, and maybe we could have gotten x plus 1. Maybe this picture captures more of the essence of the usual reparameterization trick. So now, just skipping over the details, structurally what this looks like is our solution to this, getting this quantity we want. It looks like an alternative program evaluation subtracted from the original program evaluation, this whole thing multiplied by a weight. Hopefully this sort of checks with this Bernoulli picture we had before. Does that sort of make sense? Okay. I'll actually skip this, but we have like a mathematical object sort of encoding this. And we, part of like the mathematical foundations underlying our package is that we prove that this indeed is like sort of gives you an unbiased estimate. And also remember that Bernoulli result, the derivative being 1 was not very impressive, but the point is that we care a lot about composability and like what you need for automatic differentiation in the chain rule. So we actually care about, like these scientific simulators, actually these really long Markov processes, and we'd like to say things about their derivatives. So we care about composability of this notion. Okay, so I actually read online recently like this advice that, so this is like the figure I made for our paper. And I read some advice that like your first figure should always show something like concrete, like some result from some real data. And I read that and I was like, oh crap, because this is just like an art figure. But hopefully it sort of illustrates what's going on, which is like, how should you think about, if you have a discrete random program and I perturb the parameters slightly, how should you think of like the sensitivity of this program? The claim is you should think about imagine like sort of like random walk, and like maybe you took an alternative step, and like and then that led to an alternative path. Like the difference in that paired with some weight that gives you your gradient estimate. So so we have a package which does this. So like now we just ask this question of like, can we have a numeric type which you can now propagate even through discrete random steps? And maybe I can actually try and show that off to you with a random walk. Okay, so the first thing I wanted to highlight was this notion of a chain rule or like composability. So one thing you can do, first of all, let's just make our stochastic triple. Let's just kill that. Let's make a stochastic triple, and let's put it into maybe a binomial, okay? So this is sort of the stochastic triple says, I care about the sensitivity of my output with respect to the probability of this binomial. And we evaluate it, and we get that, okay, you got 7, but maybe you could have got 8. That sort of people power stuff. So like, you originally got 7, but maybe you could have got 7 plus 1, that's 8. One thing to note here is, the range of this binomial is pretty large, even like its interquartile range is like somewhat large, yet the original value and the alternative that's considered in our scheme are actually really close to each other. And that's sort of one of our, claims to fame for like how we might get a lower variance derivative estimate, that it's sort of based on very correlated paths to the program. Like we get something very close to it. Just like in the ideal situation, the continuous setting, you have like, you're considering infinitesimal changes in the output. And then the cool thing is now we can start writing fancier programs. This program, let's write let's do a capital G of P. Maybe I have a for loop in it, And I'm accumulating samples from Bernoulli samples with probability P, and I'm returning their sum. Okay, does anyone recognize what this computes? I mean, I think maybe you all do. It's just it's the same program, right? So if I now think about putting this into here, so we're getting different random outputs each time, but it's actually doing the same thing. The derivative stuff is the same. So you can see when we got 7, it said, okay, you could have got 8 with weight 7.5, and so did this. So it's sort of nice that your AD tool, just staring only at this, can sort of do the same thing as it would have done for a binomial. Okay, now how could we make this program a little bit more interesting? We could now maybe make an inhomogeneous random walk. So that's one where your transition probability depends on where you are. So let's do something like that. Maybe we can do something like this. Does this sort of make sense? So this should be a reasonable random walk, right? Because we'll definitely go right when we're at 0. And then the farther we are from 0, we're like, hey, maybe we should go left. And there's a parameter dependence, which is nice. Because obviously, if there weren't a parameter dependence, then we don't have an interesting problem here. Okay. And now, actually, let me also ramp this up. Okay. So now let's think about putting our stochastic triple in here. Maybe 0.6 is not so fun of a value of P anymore, right? Let's try P equals 50. And what this is telling you is the picture is you sampled this random walk and you originally got 51, and maybe you could have got 52. So your derivative estimate will be 0.139. We can also, there's just all of that. I'm showing you this like underlying object because it'll talk about the package, but really the API that you ultimately want to use is maybe something like this. Okay, and you'll just have to trust me on this, but this would indeed be the derivative of the expectation of that random walk with respect to this parameter P at P equals 50. Okay. Yeah, so then I said, so again, we saw in that random walk example that we get this nice coupling. So that's again sort of the thing we're trying to push, and you can sort of see that like that can give you a variance reduction in this case. Although in general, for arbitrary programs, it's still a bit of a mixed bag. Okay, so now the last thing I wanted to talk about was this application to differentiable Metropolis Hastings. So Metropolis Hastings works like this. You are at a current sample x, and you propose a new sample x prime, and then you accept it with some acceptance probability. That depends on, so basically the setting of Metropolis Hastings is you have an intractable target density, which is intractable in the sense that you don't know its normalized cost. But you can evaluate ratios. You can say how much more likely was x prime compared to x, and that appears in this accept reject probability. And now we can think of this, for now let's focus on the blue. So this is like the original Metropolis Hastings sampling chain in blue. And now if you apply our method to it, we're going to start considering alternative paths due to the fact that maybe you accepted in the primal, but perhaps you could have rejected, right? And then what we find in this case is actually something that's really appealing to do, is to put a lot of effort into coupling like these excursions, these alternative paths you go on to your original chain of samples, such that they recouple. And intuitively, this might reduce like the variance of your estimate because you're able to consider like a bunch of them rather than just one. And in particular, like what if you're interested in like estimating expectations using the samplers, sort of a basic property you want is that the longer your chain is, the more accurate your estimate becomes of like this posterior expectation or whatever you're computing. So this is like the ergodic property of samplers. And now you might want a similar property for this derivative estimate. So you can look at the variance of the derivative estimate as the chain length increases, and it actually, it does go down, as opposed to like just a naive application of the score method. Yeah, so this is also the word often people use is consistent. And then the cool thing about this is we could just write a Metropolis Hastings code, which, like in X exponentials, you can even like use array indexing, like and differentiate through array indexing, which now makes sense because this coin is like an integer that could flip. Or like picking these X exponentials, you can just apply StochasticAD to it, and you can get a differentiable Metropolis Hastings. Okay, so very quickly about the package internals, I've sort of shown you the API. Internally, this is operator overloading, so it comes with its usual, quirks and downsides. And then one package that I, was really useful in doing this was chain rules overload generation.jl, which sort of takes all the existing chain rules, and now you can use them for writing overloading rules in your functions. You can just make a hook, which means I didn't have to like do this scan of like 500 functions, which I had to overload. Okay, in Outlook, there's really, there's still a lot of limitations of our approach. There are also sharp edges. So there's a limitations page of our documentation, and really we're trying to push forward like applications of this. And there are a bunch of things, especially like things like incorporating reverse mode and so forth into our approach. I just wanted to quickly give a shout out to like a couple other related works. Like there's also some work that a master student of Moritz's did on differentiating now piecewise deterministic Markov processes, so like processes that are continuous sometimes, sort of like these jump processes. And there's also this really nice work from the probabilistic computing group at MIT on like taking a programming language view to like this sort of problem of discrete gradient estimation. And yeah, just thank you very much. Yeah.
Thank you for the great talk. Other questions?
Hello, nice presentation. I have a question. It's a dumb question, but let me ask you anyway. Does your implementation, because I didn't have time to look at your implementation, but does implementation work for theoretically true random numbers, or does it depend on being a random number that has a seed and everything?
So the way our approach actually works, so there's a very sad flaw of our approach, which I guess I have to show, which is a lot of people write Bernoullis this way. We would drop the gradient through this just as forward diff would. So our rules are written at the level of abstraction of these Bernoulli samples that look like this. So I would say there's no limitation in terms of like what sort of RNGs we can support, but this is like the key. This is the level of abstraction at which we write our rules, and there's this very sharp edge.
I mean, to make my question clearer, does it depend on a seed? A seed, like a random seed, like normally, as you mentioned, I think you mentioned throughout your presentation that something about a seed that you try to get the derivative using, or maybe
so like
I'm completely off topic.
Sort of our derivative computation is sort of attached to the primal, right? So like our derivative estimate depends conditionally on what your what your original sample was, but we don't really fuss about how you got your original sample. So we don't care about the internals of how you sampled this Bernoulli, and therefore we don't explicitly look at the seed, but then we sort of do mathematically we condition on the Bernoulli.
Thank you.
Further questions?
Thanks. Yeah, that was a really, really great talk. Yeah, so I guess you partially answered my question. So I guess I'm wondering, so if I have a code with a bunch of different branches and a random variable decides which branch I take, in this, because of the way chain rules work, I guess I need to evaluate all the branches and then sum them up with a mask on one?
Possibly. So like the way we can currently implement such code is you could have a function such as you can sample from a Bernoulli, and then you can return something like 3/5 of x, right? Something like this. And you can flow stochastic triples through this, right? Oops. Let's see what could have gone. Oh. Gotcha. Thank you. Let's just check if the original program runs. It's one indexing. All right. Okay. Okay. So back to the question. So this is, and you can imagine implementing branches this way where you do have to eagerly evaluate everything. But in theory, like for example, we don't support stochastic triples of functions, but really this could be functions representing continuations of the rest of your program under each branch, each index on. And there's no fundamental reason to eagerly evaluate each branch. But I would say for like this coupling idea we're considering further, where we like want to couple the alternative branch to the primal branch, it's nice for them to have at least the same computational structure. So like generally we've prioritized more really driving down the variance than just increasing the applicability. So that's why I don't mind so much not having considered that case. But yeah, that's.
Thanks.
So, since it works at only a certain level of abstraction, wouldn't it silently fail if there was just a rand of nothing?
Yes.
Right?
Yeah.
Okay.
Yeah, so it's traditionally already, this is part of the limitations of nesting your approach in like a general purpose programming language, which always comes with a bunch of benefits. But there also, another approach, like the sort of like the ADA work that I briefly take is they very much care about restricting a programming language that you provably get correctness, which is also a very respectable approach. But here we have this sharp edge. Yeah.
In theory, you could probably have a set pass fix some of them, and then for some of the ones that you can't auto fix, you throw an error for. So I do think that you could like go through the code and find like a strategy ran.
I have tried to like safely error in some certain other cases. For example, the branch case, we can error for, but that rand less than p case is just really hard to handle in overloading, because like, how do you really detect that? Yeah, so I would love to handle it for an error, but I don't even know how to do that. So, yeah. Maybe, yeah.
This I can do it, right? Because you would check